because of the importance that I need to make sure everybody follow these things. This is basically the two practice we'll go through in class, but I want to make them into a homework, okay? Identical homework, okay? Identical problems, just make sure that everybody follow on the same page, okay? So I'll pass down this is due in 1 week, okay? I just want to make sure everyone is, even you haven't been in the class, this is something that everyone will be on the same page, okay? But this is identical problem. The second problem will be coming as a hacker practice, hopefully this lecture, okay? Of this lecture, okay? So there's no seriously additional work, okay? So the purpose of this practice is to show you how a local perturbation, okay? A local perturbation of H to estimate the slope or the margin, right? Have this behavior of when you decrease H, right? You improve the estimate, right? Because this is older H, right? When you decrease H. But simultaneously, when H become too small, for some functions, the round-off error will catch up. Okay, so this is, I want to make sure that everyone understand this. The order of H, big O, if you somehow didn't get introduced properly in the, say, the previous classes, this can be checked if you have plotting the error in log. Typically, this is checked in log H, okay? You should observe a slope that is the order of that big O. Okay, simple power law, right? Power law, log error. What does that order H means? Log error versus log H, okay? The slope will be 1, okay? You use the second order approximation, you will see this one to be 2, okay? But not for this problem. This problem, because the problem is quadratic. When you use a quadratic approximation, the error is 0. You should see it, okay? Until your perturbation catch up, okay? Your round-off error catch up, okay? That the second, if you use a second order approximation for a quadratic, when your function is really quadratic, there's no error. Okay, so you should see that that this one is 0, okay? Cannot be seen on the log plot, okay, until your round-off error catch up, okay? Okay, so now let's progress into the Taylor series, okay? And the purpose is to introduce to you, eventually I want to lead to something called the HP adaptivity, okay? This is the central message of this lecture. And actually, central message for the semester, okay? That whenever you use an approximation, a binary world to approximate a real world, okay? How do you control the error? There are two basic methods. H means H here. You use a perturbation to understand how your slope, your margin, your function is, okay? That's called H adaptivity, okay? The selection of H for all kinds of functions. When the ground truth is not known, what can you do, okay? What is appropriate choice for H, okay? This is one important thing. The second adaptivity comes from the order, okay? You can use different approximation. Some carry first order, some carry second order, okay? So you can use the P, stand for polynomial, okay? Polynomial order to approximate the functions, okay? From your binary computations to a real world computation, okay? For sure, this when in the simple functions, when the ground truth is known, then you don't see how powerful is this. But most of the time, when you call a fx, especially x is a multivariable, okay? You don't know the ground truth, okay? So you have to use different way to approximate the behavior, and you always have to know how good is your approximation. If you don't know, don't trust it, right? You have to have a way to test it, right? If you don't have it, then, for many, this morning I would just ask by say, have you heard about the robotic surgery? I said, yeah, I've been doing that since the old days in the first day of virtual reality. Okay, we do operation table and then virtual reality and then operate on things, and robotic arm copy the medical doctors, whatever, right? In that very simple example, if you do not control the error, can that be horrible? Right, that can be totally horrible, right? Okay, so here, we are going to these generalized Taylor approximation. You can see if I perturb the two-way, okay? Perturb it two-way, first perturb by H1, then I perturb with H2. These are just Taylor series, right? Taylor series, you can see that this perturbations is proportional to H1 times the first derivative and the H1 square half to the second derivative, and remaining it's H cube. Okay, very simple. Okay, same thing you can write it for H2. Okay, different selection of H1 and H2 will have the same behavior for this very simple Taylor expansion. Okay, no surprises, very rigorous, very general. Whatever your f is, even when your f depends on a factor of x. Okay, you have multi-variables in your independent variables. The Taylor series remain general. You can always write this, right? You can always write this. Okay, so you can write a general second order method if I know 3 points, right? If you observe these two equations, okay, second order equations, meaning that I'm going to write everything in this h square and h2 square. So if the first equation I times this, second equation I times this, I add it up together, right? Move the h to the other side, then I get a arbitrary approximation, okay? Arbitrary in the selection of h1 and h2. But the approximation is going to be second order, right? Why? Because here the second order term of h1 or h2, second order term that proportional to the second derivative of your function is cancelled. And I can always do that, right? If I know 3 points, I have the freedom of doing that to cancel one term. If you follow the procedure, if I know 4 points, I can always make a third order approximation in Taylor expansion. If I know 5 terms, I can always make a fourth order Taylor expansion that's fourth order accurate. Okay? So now the weapon in your hand, right? If I have a way to evaluate f, I just know how to evaluate it. I have no way to estimate the slope, okay, analytically. But I can estimate it by sampling, right? 2 sampling points give me first order approximation. 3 sampling points, as in here, give you second order approximation. 4 sampling points give me third order approximation. And I don't have to restrict, right? For arbitrary H1, H2 selections, I can always do this, right? So this is give you a way to use Taylor expansion to look at the simplest P adaptivity, right? When I have more sampling information of a function, I can make higher order approximation in addition to the finer approximation. Okay? Finer approximation by choosing small h. But if I have more information of different h, I can make higher order of approximation. Right? This is the important message, okay? Very simple Taylor expansion, no trick playing, okay? That I can always use simple linear algebra to create arbitrary order of approximation by knowing more sampling points. Okay, no surprises, nothing strange, okay? And you can see the previous second order term by the central difference is nothing but a special case, right? When your H1 is equal to minus H2, right, in this formula that this term canceled, right? So that's just a special case. And you can see that's the only special case. The only special case for second order approximation knowing only 2 points is the central difference, when these terms just happen to cancel each other in this case, right? So previously in here, right, this one, it's a special case, okay? It didn't violate the principle of when I know more points, I can improve the order of approximation. Okay? So you are if you have the patience to do the third order approximation, you will see that there's no accidents, okay? There's no points. You can use 2 points to know exactly the third order approximation. That doesn't exist, okay? So this simple algebra will show you that, okay? So yes?
So all you did was take so I have 2 points,
yes,
x plus H1 and x plus
yes,
H2, and
yes,
all you did was multiply in such a way as to cancel out the second the double derivative of that.
Yes, yes. Yeah. Thank you for that very accurate description. Yes, that's only that. It is because the procedure is so simple, it's so general, right? It is only that. I didn't play any tricks or any additional assumptions. If your function can have Taylor expansions at 2 different points, okay, that's the only assumption I made, then this is always rigorous, right? For sure, the range of your selection of H1 and H2 have to be in the range when F is well behaved, right? If F have a asymptotic infinity, then this won't work. Okay, so the only assumption here is that, okay, the Taylor expansion is is a reasonable approximation. Okay, but with that, this is the only information I need. Okay, for sure, I give you a lot of these crazy equations. Okay, some of them not so crazy. Okay, no, if mathematicians always can give you a equation that fail this by choice of F. That give a discontinuity at some points, and this can fail. Okay, so as long as F is well behaved, okay, when I say well behaved, usually I mean continuous, and to whatever order that I need, this derivable at that order, then this is rigorous. Yes.
But what if H is really, really small?
The runoff will catch up sometime, right?
Yeah.
Right.
But this thing won't work.
This won't work, right? Exactly that problem to teach you, right? Order approximation cannot get rid of the round-off error. There are 2 separate sources, right? One source is that when I have an H, I throw out higher order terms. That's one source of error. When I evaluate my functions by a subtraction, there's precision issues. Those are 2 different sources of error, right? So, yeah, when runoff error happens, then the order approximation not useful. Okay, that's exactly I want to tie, and this need to be so solidly in your mind. So I decide to give that homework. Okay, so you will see that when you tabulate it. Okay, you will see, oh, this is the improvement by orders. This is improvement by H. This is improvement, no improvement whatsoever when the round-off error catch up. Okay. For sure, the very last column is how do I estimate whether I'm accurate. Okay. Okay. This is very simple. Okay. So that so we see the special case in here. Okay. So okay. So now let's just as a summary as we just discussed. Okay. So we use knowledge of more points to improve the approximation order, right? So more points means more H sampling. Okay. You can approximate the approximation order. That's P. Okay. HP adaptivity. Okay. Okay. When h become very small, higher order term usually diminish, right? Because order h, when h is very small, becomes smaller and smaller. Okay, Taylor expansions, right? So this is, but not as a monotonic function, right? Because is h times your higher order derivative. So it still depends on the function. Okay, it's not that your higher order always improve monotonically. Okay, because the error still depends on the function, right? Very, very simple example for odd function, right? If your approximation function has an x squared, that doesn't matter, right? Because that derivative is 0, right? So it's not a monotonic, right? Because your error is also depends on the nature of your function. Okay, but in general, it will improve. Okay, in general, when h becomes smaller, before round of error catch up, it will improve your approximation. Although it may not be a monotonic way that depends on the nature of f, but in general, okay, when you go for finer and finer h, you will get a better approximation. Okay, higher order terms can also approximate better. Okay, but many times when it's a higher order term can oscillate, right? You approximate a functions with a higher order polynomial, and higher order polynomial have oscillations, okay? And that can happen, okay? That's just as a caveat, but it's not the critical things now, okay? The critical things is that we know that h can be used to improve the accuracy. P, the order of the function, can be used to improve the approximation error, accuracy. Okay, it's a two central message. Although these are caveat for that. Okay, there are functions that have this continuous point around place you want to estimate the slope. Okay, all this was thrown to the water. Okay, sorry. Okay, it does not converge, right? If your Taylor series at a point does not even converge, for sure, then all this analysis it's useless. Okay, I'm assuming that f is well behaved around the point I would like to do sample and approximation. Okay, function like this will screw up everything when your Taylor series does not converge. Not a surprise. Okay. So before I go into the next estimation, so just as a precaution, Taylor series is not always the best choice. Okay, it is very intuitively clear on the order. But Taylor series, from your linear algebra, you'll probably know that Taylor series is not orthogonal. Okay, 1, x, x squared, x cubed as bases are not orthogonal function to each other. Okay, saying that if I'm only interested in the behavior from -1 to 1, there are polynomials that's orthogonal. What does that mean? Each base functions, when you integrate over that same period, okay, if you integrate by itself, it's 1. If you integrate with any other function, it's 0. It's orthogonal. Okay, there are choices of orthogonal polynomial functions. Why orthogonal is important? Meaning, in the contributions, they are all independent. Right? Orthogonality means when I have the first order, okay, and it's orthogonal to the second order, all the first order information is captured in the first one because the first order term is orthogonal to the second order. When you add the second order, it won't perturb your first order approximation anymore. Okay, but Taylor series, because it's not orthogonal, when you add the x squared will still perturb your choice of x. Okay, it's just the way it is, right? Because it's not orthogonal. Okay, but there are when different approximation you can use orthogonal polynomials. Okay, to serve as a better space. Okay, better expansion so that you can converge faster. Okay, these when you do search, there's a very close to the idea of when you do search. If you do search, you can do a gradient method, right? When you do search, I want to search for the minimum. So I'm searching for something that can give me my function to be smaller. That's called the gradient method, okay? Tightly related to local analysis. During that search, if you can make each search in the orthogonal directions, that means when I search in these directions, I don't have to search this direction anymore. Okay, my next search direction is orthogonal to this. Okay, that become a name called conjugate gradient. When I search for gradient, it's one method. You can always do that. Okay, but if you make your search to be orthogonal, then it becomes conjugate gradient. Same thing here. Okay, when you make a Taylor expansion, if you make your base function to be orthogonal, then it's a better, most of the time it's more efficient, okay? Because your second order approximation won't perturb the first order, because everything first order is orthogonal to any higher order approximation functions. Okay, so sometimes this is worthwhile. Okay, if you feel fuzzy about this, fine. Okay, I will come up with much better example when the time comes. Okay, I'm just before you may ask the question, why do I have to stick to Taylor series? You don't have to. Okay, for many different functions, in a way saying that if I need to give you elliptic function, okay, then I can tell you what is the most approximate function to use. Okay, that will come later. Okay, and orthogonality many times is one thing that we desire to have. Okay, just as a feel fuzzy is okay. Just know the existence. Taylor expansion is not the only approximation. Okay, good enough. Okay, good enough. Okay, for now. Okay. So another caveat I would like to introduce is the accuracy and stability are two different things. Okay, I want to use this very simple example to tell you that accuracy and stability are different things depending on your f. Okay, so and this again will be used as an example to motivate you to understand the HB adaptivity. Okay, in the way that what is it good for. Okay, so this example teach you that accuracy, whatever you do by your adaptivity, does not affect the stability. You can have a perfectly stable method, but the accuracy is still something that you need to control. Okay, and you can have a perfectly accurate method, but if you formulate it, it's non-stable. It's non-stable. Okay, let me show you with this very simple example. Okay, so here is a functions of ft. Okay, we want to evaluate. This is a functions of time progression. Okay, the simplest functions of ft equals to exponential functions. Okay, when a is less than 0. Okay, this is the first order chemistry. They call the Arrhenius relations. Okay, you have a barrier. Okay, on the first order, how much I can go to the barrier, and you will observe an exponential decay where the a is proportional to 1 over the barrier energy. Okay, so this is something that's your basic chemistry. Most of the chemical reactions stable by these exponential functions. Okay, so you can very fast write down what is the describe, right? Why is that? Okay, that means the change in your function in time is proportional to your present concentration. First order chemical reaction. Okay, the change, the reaction rate, depending on my present concentration. Okay, that's nothing fancy. Okay, but a need to be -1. Okay, a is positive. I change faster with my concentration. For sure, that's explosive, right? That is the definition of explosion, right? So if the reaction rate become faster when it have higher concentration. So it's a positive feedback, it will grow, just explode. All explosives have that equation, okay, with A larger than 0. Most chemical reactions go to a point that's stable, okay, with A that's minus, right? So if you say my concentration and my rate, it's when there's a concentration, when the concentration get high, my rate becomes smaller. Become stable, right? So this is the so A usually for most of the stable system should be stable. okay, a less than 0, okay, this equation should lead to a exponentially decay stable system, okay? So you can immediately see, right? I can use my first order approximation to approximate this derivative. Okay, this is very familiar. You probably should have seen this in your calculus class. This is called 4 Euler, okay? The only difference is I use this term to evaluate the slope. What do I use to evaluate the present f? Okay, in here, 4 Euler is a times, I evaluate f in the previous step, okay? Backward Euler, meaning that f, I used my present value, okay? A little bit math, well, moving this around, 4 Euler is this, backward Euler is this. For the very simple examples, okay, it's just a mathematical progression, right? Once you know 0, every time you times this, right, is your next time point. Right? So for this very simple approximation of these equations that you solve, right, move this here, right, move this guy for sure is ft, right? If ft, how the ft depends on your previous time point. Okay, this is just simple algebra, lead to that. Okay, backward Euler, you have to move this around, so this is backward Euler, right? And your time progression is not a surprise. It's a geometrical series. Exponential function is a geometrical series. Right? You know that, right? A geometrical series approximating exponential functions. Okay? So not a surprise, okay? So if you progress in time, you just each time step, you times this, and then you get your next estimate. And you will find that this one can only become smaller when this is satisfied. And as long as a is less than 0, the backward Euler is always stable. Right? You can see that very clearly. Right? This one, if this is not satisfied, this term is larger than 1. A geometric series with the ratio larger than 1 is increasing, not decreasing. Period. Okay? But backward Euler, that's here, this as long as a is less than 0, your delta t for sure is positive. So this is always less than 1. Okay? So the choice of this delta t is the choice of h before. The same thing, right? I'm just looking at time. Okay? So delta t is my h. Okay? The choice of the smaller the delta t, the better the approximation. Okay, but you do the approximation differently. Okay, one can lead to unstable results. One, even it's astable, absolute stable, there's still an order that of the error. Okay, so let's see it. Okay, let's write a very simple program to see it. Right. So you know that 4 Euler is nothing but this. Okay, and let's make the time progression. Okay. By 4 Euler in time progression by the backward Euler. Okay, let's see it. Okay, let's see that if you use a first order, right, how your time progression will tell you using the both first order approximation, but formulate differently. Okay, that what is the results? Okay, let's try this. This should be the simple enough 5 to 10 minutes programming assignment. Let's do it. Okay. If you have done this before, I apologize that this is repetitions, but should be simple enough for you to do it on the fly, and you can observe that. Turn off the light. It's so bright. Feel free to move. Let me get rid of this. please feel free if you have any questions about the different setup. Okay, it's basically just every times 4 Euler times the factor of 1 minus delta t for backward Euler 1 over 1 plus delta t. Okay, that's because a is minus 1. If you're using C, it's nothing but a for loop, right? Times that geometrical series, each time 4 Euler times 1 minus delta t, that the other times 1 plus delta t. Anyone finished? First part, okay. And the second part, backward Euler should be surprising, right?
In forward, for delta t, when I'm getting 0.
Yeah, sure. Just if delta t equal to 0, it's 0 all the way, right? You can see that, okay? And when it's go to delta t equal to 2, it's totally going crazy, right? It's oscillating like crazy, right? Yes. But also important is we observe when delta t is equal to 0.5, the answer is identical to backward Euler, right? You should be able to see this immediately, right? Has to, right? So 1 minus delta t when delta t is 0.5, okay? And this is 1 over 1.5, okay? So the ratio is different, okay? But it's as accurate, you know, it's exponentially decay. Right?
But in backward, for 1 it's not 0. So it's minimum for 2. In backward Euler, for delta t is equal to 2, the value is 0.04. So that's the.
So the answer is different for sure. You times it every time. You march the time differently.
Yes.
Okay. But if you align the t point, right, delta t, it's if when delta t is 0.5, it takes 4 steps to approximate when delta t is equal to 2. Right. The true answer for sure is e to the minus t, right? So I actually know the true answer. You can see that your smaller delta t approximate your exponential minus t better if you plot it, okay? Or you tabulate it, you can see the error, okay?
So when delta t is 1, she gets 0.
Yes, 4, yeah, for sure, yeah. But backward Euler is not 0. No, it's actually still exponential decay, right? It's just that decay in a different rate. Okay, there's an error, although it's stable. Larger error, right? When you choose smaller delta t, it's closer to the true solution.
Yes.
Okay, that's the thing I want to tell you. Okay. So actually, for this simple question, even if you observed it algebraically, is that really no surprises, right? So your choice of delta t in some method can lead to unstable, okay, instability. But even for something that's absolutely stable, choice of delta t still affect the accuracy. I just want that you remember that, okay? Just implement that. I've seen it, okay? This is true and absolute truth, okay? No surprises, okay? Okay, I'll leave. If you cannot finish this in class, that's fine. Okay, something that's this is a for loop but the most important idea is that stability, okay, accuracy is accuracy. Okay, they are both dependent on how you formulate your approximation. Okay, absolute stability doesn't mean accuracy. Instability in formalism doesn't mean inaccuracy either, right? Your for Euler, when you choose your delta t appropriately, give you the right solution, okay, even though it's not the absolute stable method. Okay, so stability is stability. Okay, accuracy is accuracy. Okay, whenever you do a verification, okay, stability affect how asymptotically you go. Accuracy affect in each time point how accurate it is. These are two separate things, okay? Okay, let's go to the central message, okay, that we can understand the first step of this HP adaptivity, okay? So now, the choice of H2 equal to 2H1, okay, just for the special case before, when H2 is equal to 2H1 equal to H1 is H, okay, I rewrite this, right? I can write down this very general Taylor expansion, right? So then I know also that I have a second order using the H and 2H, right? I have a second order approximations of the same function. No tricks, right? Just this special choice, I can have 3 approximations of the slope. And I know, okay, because this is the same function, okay, regardless of what is the unknown second derivative, if it exists, it's the same number. Regardless whether this is multivariate, whether this is whatever the domain it is, right? It is, if the second derivative exists, it's the same number. Meaning that I know the relative errors if I choose my H differently, okay, or I choose my approximation differently, right? Because if the second order is something that I know, or the higher order terms is something I know, there is an unknown number, but it's fixed. then it behaves the same way. Okay? So I can get an estimate how good is my approximation in H by comparisons of the results of 1 and 2. Okay? Without knowing what is the true slope, right? I have an estimate of, if I do this by comparing the results of these two approximations, I have an idea about what is the error I'm dealing with. Okay? If I compare 1 and 3, then I have an idea about how linear is my function, right? I use a linear approximation to approximate a function, or I use a quadratic function to approximate the functions. The difference is something I can know. I know how good is my approximation without knowing the ground truth, right? When ground truth is known, you just compare with the ground truth, you have an error function that's defined. But without knowing the ground truth, if I only have sampling point, I can do this trick, right? I perturb it differently. I make my perturbation 2 times larger. And I would like to see what is my 2 times larger perturbation works. Compare with my original perturbations, I get an idea about the behavior, right? Moreover, I use the H and 2H, formulate a second order approximation. I actually even know how is my unknown fx, what's the order of change? Is it closer to a first order change or second order change? Right? Without knowing the ground truth. Right? Let me give you something even better. Okay. If I can use this P to estimate the error, okay? I approximate the same thing with different orders. That can be used to direct the choice of H. Let me say that again, okay? I can invent the method that I make perturbations, okay? I make perturbations, so I make a first order approximation and a second order approximation. I'll compare the two. I compare the two and find, okay, if they are very close, that means, no, first order approximation is good, my present H is pretty good. If my first order approximation and second order approximation are very far away, that means my H is too large. I should chop it down. Right? That's the central message of HP adaptivity. When you have more sampling point, you can, without knowing the ground truth, you can perturb the systems to know its behavior. Right? And you can make a quantitative measure how good it is and how should I adapt to the error. Okay? Take a step back and think about it. Okay? You write a program into an unknown prediction, whether it's a stock market, it's a robotic arm or something. Okay? Take a step back. If I don't know the ground truth, what is the best I can do? Inject different perturbations and observe the behavior. That's qualitatively the how you learn the system. That's probably how you learn the system anyway in your childhood. Okay, so but that's qualitative. Your computer can do better because I know the value of at x plus h and x plus 2h. I can formulate in a way I use the perturbation to learn the local behavior of the systems and know how should I choose my approximation. Okay. So this is the central. I basically say the same thing. Okay. So without showing this is a summary. Okay. That's the spirit of HP adaptivity. Okay. Let's walk through it. H adaptivity, improvement approximation by using smaller h. Okay. But remember, smaller h, there's a limit, right? You have a round of error waiting for you, right? You cannot always choose. Okay, let me just use smaller h. Can't. Okay. You have to use the appropriate h. The good enough h, okay, without you overdo it, run off error comes in, no order approximation can help you. Okay. Second, P adaptivity, improvement by approximating using a different formulation. Okay. And simple function like this, for sure, when the order is correct, you will get exact solution. Okay, for sure, that's the question is so simple, then okay. Then the right approximation function is the function that you get zero error. Most often this is unknown, so this is how you need to be evaluated, okay? And most of the time, evaluation F is possible but expensive. Okay, if it's so cheap, then great, okay, I'll evaluate a lot of copies. But many times, the evaluation of F is doable but computationally expensive. Okay, so whenever you do these perturbation and trials, you want to do it the least number of times, right? Because if you do a lot of times, it's just computationally expensive. Let me give you examples, okay? Your circuits, okay? If what I'm interested is the current going through here, going through this low resistor, I know this current depending on all the voltage here, okay? If I know all the voltage here, I can solve the equations and know the current here. Okay? Your F is the current through the load. Your X is all the voltage factors in these things. Given a voltage on every node, can I solve this? Yes, I can. Okay, this is a differential pair. If you try to find what it is, small signal differential pair. Okay, so just F is doable but expensive. Okay, robotic arms. Okay, so your destination, your F is how far you are away from your target. Okay, this usually should be a F. Now I have 3 variables, right? Because it's if you're just interested in the distance, it's 1. Okay, but it's a factor, right? It's a factor is your F, and it's depending on all the different solid angles of your robotic arm joints. Okay, this is a famous formulation of a snake arms, right? If I know all the solid angles in each joint, do I know the positions? Yes, I do. Okay, but the evaluation of that is expensive. And if I know all these errors, okay, all these things, how much error is in the computation? That's so critical for all the application, right? Imagining this is the differential pair feeding to the motor of your airplane flap, right? And you control it dynamically, and somehow the accuracy is not enough or not respond fast enough. The airplane, who knows where it goes, okay? And this, if you are at beginning, this is your robotic surgery. You know, is try to zap that thing, a tumor, something you try to cut, but the computational algorithm, you don't know the error. Okay. Horrible, right? So any software you try to do to interface with the real world, find a way to estimate the error. Find a way externally, okay, not just externally. In your software, whenever you write it, that is the number one thing in your mind. How do I write something I can verify? Okay. If you do not have that, not an engineer. Okay. It's not you hack a program and just hope it works. Okay. That's just not right. Okay. Whenever you write anything, right, think about testing and verification first, right? Each step, how can I write a test? Each step, how can I write a verification? Each step in the approximation. Without knowing the ground truth, I want to know how well I'm doing. Okay. And this perturbation method is the first step, right? Without knowing the ground truth, I perturb it differently. I know something, right? I know something quantitatively. Okay. That'll be it for today.